we have an alkyl halide, and then we have a reagent. That is a methoxide. Methoxide, is it something would you consider strong or weak? This oxygen is negatively charged, just like sodium hydroxide. You don't try to put your finger into it, right? I mean, unless it's a really diluted, then we can do it. But if you don't know, it's like a very viscous solutions, and then your friends give it to you, and you put your finger into it. Would you do it? It's a strong reagent like that? No, right? Hell no. So, oxygen, when it's negatively charged, that's the dangerous thing. When they become neutral, like an alcohol, water, fine. I mean, I'm pretty sure that something may happen, but you're not going to get the first or second degree burnout of it. But this one, it can take the skin off. You can even dissolve the tissue if you leave it long time. So this is something that you don't want to think about, especially if really, really strong hydroxide solution. You got to treat it carefully. I mean, I'm not talking about the solution that you're using in the lab. That's dilute, nothing really much going to happen to you. But sometimes you got to use really thick viscous solutions. You heat it up, and yeah, everybody's scared of it. Anyway, that's a very strong base, and that is going to be either attacking directly or picking up the proton. There's no proton there, right? There's a proton center. There's no proton there. So low elimination could potentially happen on this side because these are all no hydrogen there. But the hydrogen is on the other side. Once again, what is an E? Not to name it C, right? Deuterium, right? That's a heavy hydrogen. You may think that it's the differently colored hydrogen, or heavy light hydrogen, heavy hydrogen. Anyway, that's what it is. Now the question is, then is it SN2 happen or E2 happen? That's the question. Do you think SN2, E2 will happen together? Yeah. Especially if this alkyl is a tertiary alkyl halide, then SN2 will be shut down. But this is not tertiary, that's a secondary. Secondary alkyl halide, SN2 still can happen decently, and E2 still can happen decently. So do you think SN2 will happen to this molecule? Many of you will nod your head, but I'm saying no. It's all because you got the protonase center next to it. This will basically prevent this one nucleophile coming in. Remember that we got example there. The T-butyl next to sitting on the primary position, SN2 will not happen because of the Berkey substituents next to it. So that these subpositions will shut the SN2 down, even though this is secondary. So only thing it can do, it can either come pick up this hydrogen or pick up that hydrogen. So when I said that's a hydrogen, now you understand, right? That's just the heavy hydrogen, right? So that's why they want to put a different one. And then the question is, which one will it lose? Is it going to lose the lighter one? Is it going to lose the heavier one? How is this going to happen? Right? That's the question. So in order to see that, it's a six-membrane cyclohexane. And I just want to tell you the answer first. They're going to lose a heavy hydrogen. Only the heavy hydrogen. Only. It's not like this is the major, the minor will happen. No. They're not even make a minor. This is the only one you're going to see. So why you're going to see the heavy hydrogen loss, not the lighter one, is because that's the one sitting the trans to the bromine. That's the key. In the case of the open chain structures, anti-coplanar is your guiding principles. Cyclohexane, anti-coplanars are something a little difficult to see. It's sort of equivalent to trans-diaxial. It's the same thing. Yes.
What the deuterium was available? It was there, and you only have the hydrogen.
You mean these deuteriums are not there? That becomes like a methyl groups?
Yeah.
Yeah. Good question. We'll get to that. Right there. That is actually what we make a question a lot of times. So we're going to have a question, slide coming up in a minute. So we'll get there. But the first thing is, I see that anti-coplanars are really, really hard to see in the cyclohexane, right? So it's good to use a trans-diaxial as your guiding principles. So how that works here? You know the cyclohexane never becomes a flat in actual structures. We talked about that, right? The chair conformation. If I'm asking you the most stable chair conformation, I'm pretty sure you're going to say duh because you forgot. But if you kind of are looking back, we want to make sure that our substituents sitting on the equatorials are better, right? Not axial. So the bromine sitting on the equatorial makes it most stable conformation. But when you're sitting in the equatorial side, do you see any of the hydrogen exactly lined up the bromine bond for the bromine? They are angled by this bond and that one angled. This one's and that one's an angle. There's nothing that really aligned. So in this conformation, E2 elimination is impossible. I'm not saying difficult, impossible. But chair conformation is not frozen to the one chair. It can flip to another chair by flipping this corner and that corner's up. Then we can have another chair conformation. That makes a bromine goes axial. That means that this chair conformation is less stable, but it still can be in these forms. Once they get the bromine in the diaxial positions, now we got deuterium lined up. So that's why anticoplanar in the chair conformation is called a trans-diaxial. It's a trans, and this is axial, that's an axial. Trans-diaxial. We are looking for hydrogen in the trans positions. This is the bromine, trans to that is a that hydrogen, not this one. That's a cis, that's a trans, right? I mean, you want to draw this chair conformation probably, but who has the time? So you can just think about, yeah, the one, the trans, that's the one that's going to go up, and that's going to be good enough, I guess. So same as anticoplanar, it's just translated to trans-diaxial with the cyclohexane system. So now you see that why the bromine is lined up and then the deuterium is lined up, not the hydrogen, right? It's because they're trans. So what happened was the base come pick up this deuterium, makes a bond, that goes out. So that's why you only get that. That's the only one you're going to get. So this type of question is the one that you're going to pay attention carefully because this is asking you to find out anticoplanar, which is a trans-diaxial cyclohexane system, to get the right E2 elimination product. Okay. We're going to go over a lot of different questions for E2, these anticoplanar things. It's already showing you what you're going to get. So this is not like you have to predict this thing. This molecule is a chiral centers here, chiral centers there. This is actually a chiral molecule. And then if you treat this one, you get only this. First of all, why it doesn't do SN2 reactions? It's because that carbon is a pre-statically hindered. So it's not really good for the SN2. E2 still can possible. This base but pick up the hydrogen, not the hydrogen, the same carbon. I've been telling you, we should make an adjacent carbon because you cannot make a double bond with just one carbon. Right? In order to make a double bond, you need two carbons. One side is a one with the bromine there, the other side is the one with the hydrogen. So that's why the adjacent hydrogen, not this one. The base is not going to pick this one, and then you're going to make a double bond by just one carbon. Impossible. So don't even try that. Adjacent carbon, right? So base is going to come, pick up this hydrogen, and then double bond is going to form. This comes out, and then you see that these two phenyl groups on the same side. Then this phenyl should be here, so you should get cis. It looks like by the drawing that you were given. But what's missing here is this hydrogen and that bromine bond. They are not lined up. They are not lined up. We are tricking you. We are tricking you to put the wrong answer by putting these two things are lined up there. So we asking you, do you understand anticoplanar? Down to your bone. That's what we are asking here. So a lot of people see this thing, they just take it out, make a double bond, two phenyl group the same side. Oh, by the way, what is in the pH with the phenyl? I've been telling you, the organic chemists are, they are very lazy people. They don't want to throw the 6-member ring with the benzene, they just put that as just a pH. It's mean as a phenyl. But 2 phenyl groups on the same side, but you know that's not going to happen. You get a trans, only trans. Why you get only trans? Because the reaction doesn't happen. So in this form, so what happens is you gotta be seeing that this carbon hydrogen bond and the carbon bromine bond should be lined up, anti-coplanar, right? Anti-coplanar. In order to make anti-coplanar, we gotta rotate this wheel this way, right? So this phenyl group is gonna go behind the spring because it'll be rotated. And then now this one is lined up, so we take it out, double bonds forms, this one goes out. 2 phenyl groups are on the opposite side. So you get trans products, not cis. We always give a question like this, so you can write it into the chat right away. Yes.
What if you instead rotated them?
It doesn't matter. You can put this one without that one go down, doesn't really matter. As long as they're opposite side, you get the same answer anyway. Yeah. This is something that you need to think about. What if you want to get cis? What if you want to have a cis? Then what starting material do you have to have? What starting material, what stereochemistry do you have to have here to make a cis product? Cis means it's 2 phenyl on the same side. It cannot be this because that is the one they're giving first, trans product. If you want to get the cis out of it, then what is the starting material? So that's something you got to think about. I'm not going to show you. There's something you have to think about that.